Magnetic Field Lab by Drew Pelchovich. In this experiment, I used a bar magnet and a magnetometer app on a smartphone to calculate the magnetic field due to a permanent dipole magnet. In order for the experiment to be as accurate as possible, I had to align the phone according to Earth's magnetic field as best as possible. When doing so, the Y component that was read on the magnetometer was 48.5 microteslas, whereas the true value of the Earth's magnetic field in Atlanta is 49 microteslas, so the approximation was very close. In this experiment, I used two equations to calculate different variables. The perpendicular dipole approximation was 1, and by substituting my R values and my magnetic field values from the experiment, I could calculate a dipole moment value of 5.454. Second, I also used the magnetic field equation B bar equals KR to the power of n in this experiment, which could be better seen on the next slide. And finally, an observation during the experiment was that every time the magnet came closer to the smartphone, the X component of the magnetometer grew very rapidly in accordance with the magnet being moved closer. Data collection. Here was the data collected from the experiment, with the different R values listed and the different corresponding bar magnet values listed. And the average values are listed in blue as well. As you can see from the data that is put on the graph on the right side displays the equation magnetic field equals K times R to the power of n in the form of the slope equation y equals mx plus b, where the y-intercept can be interpreted as the value ln of k, and the slope can be interpreted as the value for n. In this case, the value for n was negative 3.07. Also, according to the data that are collected, the value on the bottom right-hand corner demonstrates the experimental value for the magnetic field off-axis. In my experiment, the magnetic field value was 40.633 microteslas. Here was the code that I wrote to model the experiment using GlowScript. Each observation point has its own arrow and used the function dipole B, which was created in lines 12 through 16, to model an accurate magnetic field at said observation locations, including magnitude and direction of the magnetic field at these observation locations. And finally, lines 61 through 67 show how to calculate the magnetic field and the magnitude of the magnetic field at a 45-degree angle off-axis from the magnet in the center. Here is the model of the code from the previous slide. And as you can see, the arrows point in the direction of the magnetic field at the said observation locations. All the arrows, however, are scaled up from their original values in order to be seen on the same field as the magnet. In addition, the calculated magnitude according to the computer code was 4.918 times 10 to the negative fifth. Compared to my original value of 40.633 microteslas, these were fairly accurate. If the experiment did not compensate for the magnetic field of the Earth, then the magnetic field values that I calculated in the experiment would have been greater than the true values, because in this case the Earth's magnetic field would have added to the total field calculated. The reason in the experiment for aligning the phone with the Earth was to make sure that the only value in the X component was the magnet, not the Earth plus the magnet. If the experiment did not align for these values, then the experimental values would have been very off base. The second question is, what if two identical magnets were stuck end to end? In this case, in an ideal world, the number for the magnetic field would double, because double the magnetic dipole moment would double the two magnets stuck together. However, this isn't a perfect world, where S, the distance between the North Pole and the South Pole, can be taken to be much less than R. This means that in an experimental sense, two magnets stacked on top of each other would also have a larger S value since there would be a greater distance between the North and South Pole, meaning that the experimental value for a magnetic field would not be quite 2 times the strength of one magnet, but it would still be greater than the strength of one magnet. In conclusion, the purpose of this experiment was to show how to calculate magnetic fields using a smartphone and a bar magnet, and comparing that value to a computer code simulated value, and seeing how accurate the experimental value could be to a calculated value on the computer.